When we create I/O actions that may require I/O, we risk running into all kinds of errors. For example, when we use write file, we can run out of disk space in the middle of writing, or the file might be write protected. While these scenarios are not super common, they are definitely possible. We could have potentially encoded Haskell functions like read file and write file as I/O operations that return either. However, there are a couple of issues here. The first one is that composing I/O action becomes more difficult. For example, previously we could have easily written a flow like this: read file first and then write file with the same content. But now the types no longer match. Read file will return an either read file error or a string when executed, but write file wants to take a string as an input. So we are forced to handle the error before calling the write file. One way to handle this is by using monad transformers. Monad transformers provide a way to stack monad capabilities on top of one another. They're called monad transformers because they take a type that has an instance of a monad as an input and return a new type that implements the monad interface, stacking a new capability on top of it. For example, if you want to compose values of a type that is equivalent to I/O of either error or A using the monadic interface of the function bind, we can use a monad transformer called ExceptT and stack it over I/O. Remember that a new type is a new name for an existing type, and if we substitute E with an error and M with I/O, we get exactly I/O of either error or A, as we wanted. And we can convert an ExceptT error I/O A into I/O of either error or A using the function run ExceptT. ExceptT implements the monadic interface in a way that combines the capabilities of either and whatever M it takes. Because ExceptT EM has a monad instance, a specialized version of bind would look something like this. It takes ExceptT, it takes a function from an A to another ExceptT, and returns an ExceptT. And note that M in the specialized version still needs to be an instance of a monad. Let's try to implement bind manually to see how it works. So we have some I/O of either error or an A, and some function which would apply to it. First, we bind X to the either error A that's produced by I/O. Because it's an either, we can pattern match and see which variant we got. It's either a left error or a right of some sort of result. If it's a left of an error, we just propagate an error because we have to return an I/O again. We lift it using pure function. And if it's some sort of result, then we can apply the f function to this result. Applying the function is going to return another I/O, so we don't have to lift or do anything else with it. And note that we didn't actually use the implementation details of error or I/O, because error is not mentioned at all. And for I/O, we only use the monadic interface with a do notation. The other implementation detail didn't matter. We could write the same function with a more generalized type signature. We can easily replace error for a generic E and it compiles. We can also replace I/O with M, but now the compiler complains that there is no monad instance, and it suggests a possible fix of adding the constraint. And note that in this case, X has a type either E or A. And because new type ExceptT is a wrapper around M of either EA, we can just pack and unpack that ExceptT constructors and get the bind for actual ExceptT. We'd have to wrap the result in ExceptT, and when we want to unwrap it, we run the ExceptT to get this inside. And we have to run the ExceptT to get it out of the FA. Note that when stacking monad transformers, the order in which we stack them matters. With ExceptT error I/O of A, we have an I/O operation that, when run, will return either an error or a value. ExceptT can enjoy both worlds. We can return an error values using the function throw error, and we can leave functions that return a value of the underlying monadic type to return a value of ExceptT EMA instead. For example, if we have a getLine function that returns I/O of string, we can lift this getLine and get a type ExceptT E I/O string. Actually, lift is also a type class function from monad trans, the type class of monad transformers. So technically, lift getLine has a more generic type, but we are specializing for concreteness right now. Now, if we had read file and write file functions that return ExceptT, we can compose them again without issues. Well, almost. Remember, the error type E in both the case either and except must be the same between composed functions. This means that the type representing errors for both read file and write file must be the same. That would also enforce anyone using these functions to handle these errors. Should the user who called write file be required to handle a file not found error? Should the user who called read file be required to handle out of disk space error? There are many more possible I/O errors. Network unreachable, out of memory, cancel thread. we cannot require a user to handle all these errors, or even cover them all in a data type. So what do? We give up on this whole approach for your code and use a different one, exceptions. The control exception module provides us with the ability to throw exceptions from IO code, catch Haskell exceptions in IO code, and so on. For example, we can use throw.io to throw these exceptions, catch them, takes the computation to run, and a handler to invoke if an exception is raised, and try. That can convert an exception to an either. The important part of this type signature is the exception type class. By making a type and an instance of the exception type class, we can throw and catch it in IO code. So let's give it a try. In the following module, we create our own exception for 0 case or for an odd case. To make it a Haskell recognizable exception, we have to create an instance of exception for our data type, and then we can use it in our IO code. In this example, we throw one type of error in case n equals to 0, and different kind of error in case n is odd. Otherwise, we print it. Note that we use a new syntax in here. These are called guards. It's just a nicer syntax around ifs and else expressions. Using these guards, we can have multiple if branches, and finally use else branch by using otherwise. After each guard, there is a condition. After the condition, there is equals, and then the expression, the part after then in the normal if expression. So the function has these checks, like if it passes, we do this, if this passes, we do this, and otherwise we do this. We can catch these errors using catch. We have our expression that's gonna throw an error, and the handler, which depending on the exception or a variant of our ADT, is gonna do different things. It doesn't matter what, it's just an example. There is another new biz we have not seen before, a lambda case. It's a different kind of syntactic sugar to save yet a bit more characters. Instead of writing the full case, we can just write case. This requires enabling the lambda case extension. Haskell is a standardized language. However, GHC provides extensions to the language, which are additional features that are not covered in the 98 or 2010 standards of Haskell. Features such as synthetic extensions, like we saw with lambda case, extensions to the type checker, and more. These extensions can be enabled by adding language pragma with extension name to the top of a Haskell source file, and note that language part is case insensitive. Usually you're gonna see people writing them all caps, and sometimes all lowercase. But they also can be enabled globally for an entire project by specifying them in the default extension section in the Cabal file. The list of Haskell extensions can be found in the GHC manual. Feel free to browse it, but don't worry about trying to memorize all the extensions. Of course, this example would work much better using either and separating the division and printing, like we talked about functional caller in ParserShell before. But as an example, it works. We created a custom exception and handle it specifically outside an IO block. However, we have not handled exceptions that might be raised by put string line. What if, for example, for some reason, we close a standard output handle before this block? Our program will crash with an error. Okay, how do we know which exceptions we should handle? Some function documentation include this, but unfortunately, put string line does not. We could guess from the list of instances the exception type class has, and seems like IO exception fits. And how can we handle this case as well? We can chain catches. So for example, we can check if the error was an illegal operation on the standard error handle. In this case, we cannot write to standard error because it's closed. Note that we use the scope type variables extension to be able to specify types inside the let expression, lambdas, pattern matches, and more. In these cases, we have to restrict the error to IO exception. Or alternatively, instead of catches, we can use more convenient function catches to pass a list of exception handlers. As an aside, handler uses a concept called existential quantified types to hide inside a function that takes an arbitrary type that implements exception. This is why we can encode a seemingly heterogeneous list of functions that handle exceptions for catches to take as an input. This pattern is rarely used, but it's included here to avoid the confusion. And another alternative, if we want to catch any type of exception, we have to catch some exception, which is sort of a grandparent or parent of all the exceptions. Another function worth knowing are bracket and finally, which handle resources acquisitions more safely when errors are present. In our app main file, we do a small ritual of opening and closing handles. We can try to use bracket to make sure that we always close a handle afterwards, even if an exception is thrown, and avoid closing the handles for standard input and output cases. First, we can create a function with input handle. We use continuation passing style to pass a function that takes a parameter to a function that produces a parameter and calls it with that parameter. Well, meaning that here we pass an action, which is the next step we want to do. It takes as input the value we produce, uses it, and then returns control for us to clean up afterwards. The important part is that standard input didn't change, but in case of input file, we use a bracket. Bracket allows us to use the file safely. It takes a functions to open the file and close the file, and it guarantees that when we operate on the file, regardless if we get exceptions or not, the file is going to be closed. And we do something similar for the output handle. We pass it a function, which is an action, that's gonna be run when we get the handle of the file. In case of output file, we still check if the file exists, if we can open it or not, and then we use bracket to open the file, give us a handle for our action, run the action using the handle, and then bracket is gonna close the handle, regardless of successful result or failure, or an exception. So how do we use these two functions? We use input handle, output handle, and with these handles, we can convert single title and make sure that we can take the input safely, do the conversion, and then put it into the output safely. And in case of any exceptions along the line, all the handles are going to be closed safely. And if this sounds like too much stuff, know there are functions that does similar things to what we do in opening file and closing, which is called with file. And in general, keep an eye for functions that start with the prefix with. They're probably using the same pattern of continuation passing style. The idea is that we as a users write actions and we care about actions, and then the libraries or these functions take care of opening and closing the resources. In summary, exceptions are useful and often necessary when we work with I/O and want to make sure our program is handling errors gracefully. They have an advantage over either in the way that we can easily compose functions that may throw errors of different types, but also have disadvantages of not encoding types as return values and therefore not enforce us to handle them. For Haskell, the language designers have made a choice for us by making I/O use exceptions instead of either. And this is what the author recommends for handling your own effectful computations. They also suggest that either is more appropriate for uneffectful code because it forces us to acknowledge and handle errors eventually, thus making our programs more robust, and also because we can only catch exceptions in I/O code. In the next part, after this long info dump, we'll practice what we've learned and do some coding.